rational function is a polynomial divided by a polynomial. And remember, a polynomial is an algebraic expression in which all of the exponents on the variables are whole numbers. So sometimes I actually even have separate terms, and then the last term is a polynomial divided by a polynomial. But I could still get common denominators and put that all together, and it would still fall under the classification of a rational function. Now, when we're graphing rational functions, we're always going to set up with the same outline of information we want to gather. But what happens in the specifics of the problem as we gather that information can sometimes give us some little anomalies that we need to be careful about when we're graphing the rational function. In this video, we're going to look at sometimes we find that the graph will cross a horizontal or a slant asymptote. So how do we find that value of x, asymptote, where the graph actually goes across it? Let's look at the example. So here my function is f of x equal 2x squared minus x minus 1 over x squared minus 4. With our outline of our rational functions, we first want to find the y-intercepts by setting the x equal to 0, the x-intercepts by setting the y equal to 0, the vertical asymptote or holes in the graph, vertical asymptotes happen at values of x that make the denominator 0 but not the numerator. And holes in the graph happen when you have a value of x that makes the denominator 0, makes the numerator 0 also, but after you simplify it, it doesn't make the denominator 0 anymore. And then fourth, horizontal or slant asymptotes these we are going to get from long division, and in that long division we'll be able to see if our graph crosses the horizontal or slant asymptote. Graphs will never cross a vertical asymptote. There won't be a point on it. There'll be graph on either side of it, but there won't be a point on it. And for horizontal or slant asymptotes, sometimes you might have a point on it, because they really tell you more the end behavior of the curve than actually what's happening like in the midst. And then 5, we always like to get some points, so we'll generate points. So ordered pairs, and plot it out. So first up, y-intercept, put 0 in for the x's. So y is equal to 2 times 0 squared minus 0 minus 1 over 0 squared minus 4. Well, that's really negative 1 divided by negative 4, and they don't divide any better or simplify any better, except for the simplification that negative 1 over negative 4, negative divided by negative is overall positive, so that's a positive 1/4. When 0 goes in for x, positive 1/4 is what you get for y. Next up, x-intercepts. They're values of x that make the top 0 but not the bottom, because we get them by setting 0 in for y. On the left side you put a 0. But the only way a fraction can come out to be the answer 0 is if the top of the fraction, the numerator is 0, but the denominator is not. So like 0 divided by 7, that's 0, right? But if I have 0 divided by 0, you can't do that. Or if I have 5 divided by 0, you can't do that. So really we can find the x-intercepts by setting the numerator equal to 0, and then checking to make sure the x's we find by setting the numerator equal to 0 do not make the denominator 0. Now this is quadratic, so I could solve it by factoring or the quadratic formula or completing the square. This one actually does factor. It factors as 2x and an x, and then I need to make the outers and inners be the factors of the last, be factors of negative 1, so that when I multiply out the outers and the inners, I get a negative 1 middle coefficient. Well, it needs to be negative, so I need the negative to be the largest of the multiplication, and then plus 1 in the other. Set each of these factors equal to 0. I get 2x plus 1 equals 0. Subtract 1 and divide by 2, x equal negative 1/2. Or add 1 to both sides, x equal 1. Now, does 1 make the denominator 0? No, so it is an x-intercept. 1 going in for x will give me 0 out for y. Does negative 1/2 make the denominator 0? No, so it is an x-intercept. Negative 1/2, comma, 0. So it is the x-coordinate of an x-intercept, and the x-intercepts are actually these ordered pairs. Okay, vertical asymptotes are holes in the graph. Well, they happen for vertical asymptotes if the denominator is 0, but the top isn't. So I start this process by setting the denominator equal to 0. So I take my x squared minus 4, set it equal to 0. This one I can solve by factoring, or I can solve it by adding the 4 over and taking the square root of both sides, as long as you remember the plus or minus when you do that. Either way, your solution to x squared minus 4 equals 0 is x equal 2, x equals negative 2, and when I run those through the numerator, 2 doesn't make the numerator 0, and negative 2 doesn't make the numerator 0. So I get 0 in the bottom, but not 0 in the top, so I know I have vertical asymptotes there. To see an example where there's a hole in the graph, just look at the description of this video, and I've put a link in there for a video I've uploaded with that situation. Now, horizontal or slant asymptotes, I need to find them from long division of my fraction. So I'm going to take the x squared minus 4 and divide it into the 2x squared minus x minus 1. Make sure they're in descending order. If in my dividend I have any term that's missing, I'd scoot over and leave a space. Now we start by taking the first term of what we're dividing into, this 2x squared, divided by the first term of what we're dividing by. So 2x squared divided by x squared is 2. Multiply it through. 2 times x squared is 2x squared. 2 times negative 4 is negative 8. Then you subtract, and if you've forgotten polynomial division, I also have a link to another video with polynomial division. Combine like terms, the x squareds cancel. I bring down the negative 8x, and then negative 1 plus 8 is a positive 7. And this degree in my remainder is smaller than what I'm dividing by, so my division is done. And y equal, what's in the quotient is my asymptote, and it's y equal a number. So my asymptote is y equal 2, which is a horizontal line at y equal 2. But when my remainder has a letter in it, that's when I have a place on my horizontal asymptote that the graph will cross it. And in fact, it will have a point on that horizontal asymptote when I take this expression from my remainder and set it equal to 0. So negative x plus 7 equals 0. Add the x to both sides, I get at x equals 7. So at 7, comma, asymptote. And my asymptote value is y equal 2. So at 7, comma 2, I will have a point on my horizontal asymptote that the curve will cross it. So let's go ahead and put this information on the graph. We have 0, comma 4 is, we have 0, comma 1/4 is a y-intercept, so don't go left to right, go up 1/4 and draw a point. We have an x-intercept of negative 1/2, comma 0 and 1, comma 0. We have vertical asymptotes at x equal 2, as well as x equal negative 2, And notice intercepts are ordered pairs, asymptotes are equations. Then I have a horizontal asymptote at y equal 2. And then I have a point that the graph crosses the horizontal asymptote at 7, 2. So 1, 2, 3, 4, 5, 6, 7, 2. Now when we look at generating ordered pairs for this graph, you just want to plug in x's that are left of the leftmost information that you have. So here it's left of -2, so like -3, -4, etc. Between each set of the vertical asymptotes and right of the rightmost. Now if we go through and get those values and put them on a table, we could certainly take our graphing calculator and in our y equal, put in the numerator and in parentheses, put your numerator, divide by, open parentheses, and put in your denominator. And then go to the table function and get values for your ordered pairs to help with the points. So -1, -2, we're going to put in -3, -4, maybe -5. So when x is -5, I get a y value of 2.57. When x equals -4, I get a y value of 2.91. When x equals -3, I get a y value of 4. And when x equals -2, I get an error, because that's where I have an asymptote. So if I go -1, 2, 3, 4, 5 and up 1, 2.5, I see that I'm about there. And that tells me that left of that vertical asymptote, I have a curve there. And remember that your function approaches but doesn't go a point on the vertical asymptote, and it'll only have a point on the horizontal asymptote where you found it did in step 4. Now in between these pairs, I already have these points, so I'm not going to generate more. I'll just go ahead, and it won't go up and squiggle in a corner. It'll have to come from the asymptote, go through those dots, and then go back down. And then if you also generated ordered pairs on the other side, x equal 1, 2, 3, at x equal 3, if you look on your table, you'll get that you get 2.8. So x equal 1, 2, 3, get 1, 2.8, you're above here. So your graph kind of comes from the vertical asymptote. It goes close to the horizontal, but then it goes under the horizontal and then attracts back to that horizontal asymptote after it bumps down for a bit and then goes up. And so this part is that part that would be hard to tell if you just looked at the graphing calculator, but definitely shows itself in the work of the equation and the setup work, so that we know that we're actually giving an accurate picture of the function.